Thanks everybody for joining tonight.
We're recording.
Are we recording now?
Yes.
You
Well, I
cut
can
this part
edit it
later.
out.
Yeah,
I'm
cut
not
this
gonna
part
cut
later.
it out.
Thanks everybody for clustering in that back corner. Make
Cool
it easier
kids,
for
right here, yeah.
Andre to project. This is the third meetup that Andre's hosted here at our office. My name's Tony Zappian. I'm the co-founder of Tovi and the CTO. And we build an online health and wellness product that we deliver to the corporate market. So we sell our product to companies and they give it to their employees as part of their benefits programs. And we develop highly personalized health improvement plans for the employees. We share office space with Jonathan's company, which is called Tundra Technical. So before I turn it over to Andre to jump into the talk, I'll let Jonathan come up and just introduce his company. And we can also thank them for providing all the food and beverages tonight.
Yay.
More than welcome to help yourself with sandwiches and pork, beer downstairs. And Tundra is an IT staffing company that's Canadian. We started in 2004 when I was a small child. And we started in Toronto. Our headquarters is still in Toronto. And we have offices in Ottawa now, Montreal, Quebec City, Calgary, Vancouver, all across Canada, as well as the States and overseas. Tundra India is one of our more recent endeavors that is very successful. There's a lot of IT professionals coming out of India, and you know it's a big market. And so in Ottawa, we're going after public sector primarily. I don't know if any of you guys are interested in that, but you know, security clearance is very important. It opens a lot of doors for you here in Ottawa, and we're more than happy to work with all of you. And I'm the security official actually here for Tundra Ottawa. So if that's something that you haven't looked into or gotten, I'm more than happy to help you through that process as well. Like I said, it opens a lot of doors. If you're interested, permanent contract, long-term, short-term, whatever, incorporated, not, it doesn't matter. We're more than happy to work with you and further your career. The idea is that my job personally as a recruiter is more for you guys. Every day when I go in, I'm looking to connect someone with a job that mutually benefits both myself and them. And my account managers are looking for clients who are looking for someone who can do the job for the price they want to pay. So if they're doing their job right and I'm doing my job right, everybody's happy and it's a mutually beneficial relationship. There's a lot of negativity about recruiters on LinkedIn, but I'm on LinkedIn and I'm more than happy to connect with all you as well. And prove them wrong. At the end of the day, it's the only good business is mutually beneficial business. So, I appreciate Tony hosting us, and I appreciate Andre hosting us as well. And I'm planning on coming to these once a month. Meeting you guys, socializing with you guys, hopefully talking to you guys before you leave tonight on a one-on-one basis, and getting what you want to do with your career and helping you do that. So, I appreciate Tony hosting, and I'm glad to be here.
Great.
Excellent.
You can also drop by any time and talk to Jonathan about your trip downstairs.
Oh yeah, the keg is always flowing.
Yes. Excellent. Hello. I am Andrei Drozdyuk. I work at the National Research Council of Canada, and I'll be talking today about recovering from system failure. It's going to be a very exciting talk. Okay, so let's begin. I would like you to imagine that you are living in 1969. You are a team of software developers. We are all together, and our mission is to launch a space rocket to the moon.
What kind of drugs are we
Any drugs you like. So we have been working on this project for years now, and today, July, is the day that we launch a rocket. And we gathered together in the mission control room in Houston, and the rocket is launched and everything is okay. Success, it's flying. So my first question is, who is confident that this rocket that you built software for is going to make it to the moon? If you were writing the software, would you trust life of 3 astronauts to your code? Right? This is the question we're after today. And we'll continue following the rocket as we go throughout the presentation. The outline is pretty simple. We'll look at different types of bugs you can encounter in software. We'll look at what restart-only software means. We'll look at the notion of failing fast and then the happy path. And we'll look at how to do error checking, how to handle external system failure, how to handle failure in long-running processes. Then we'll take some questions, and in conclusion, we'll look at the software that we wrote for this spaceship and see how it actually works, because maybe we forgot because we got drunk.
You look very young for your age.
Thank you. Thank you. So, the jacket got older, but I remain the same. So the Apollo 11 spacecraft used only 152 kilobytes of memory, which is, I don't know, pretty amazing, I think. But this is our accomplishment because we wrote it.
Yeah.
So what are the different types of bugs that can occur in something like a operating system for a spaceship, or the software that you write every day in 2017? There are two types of bugs that can happen: Bohr bugs and Heisenberg bugs. So Bohr bugs, what are the Bohr bugs? Bohr bugs are solid, observable bugs that are easily repeatable. This is the bugs that you think of as bugs. This is when somebody opens an issue and says, oh, this field is not responding or something like that. You go and you fix it, and you can easily repeat it in your own testing development environment. The easy way to remember Bohr bugs is it's the bugs that are boring. And they're named after Niels Bohr, who developed the atom model, right? So what are the Heisenbugs then? The Heisenbugs are the opposite. They are unreliable bugs. You can't rely that they will happen again. They only occur in there's certain conditions, like the expression once in a blue moon, that's reserved for these bugs. And when you observe the bug, if you try to log it, you might actually cause it to go away. Exactly. You might, for example, make a concurrent system non-concurrent, or a parallel system non-parallel, and so the bug concurrency issue goes away. So these bugs are very unreliable, let's just say. So what is the frequency of these bugs? When you're developing software, you're coding there, drinking coffee, the regular software development cycle. You run the program, it breaks, you fix the bug, you run it, it breaks. So these are the Bohr bugs that you're encountering, because you can easily reproduce them all the time. They happen all the time when you're developing. And what about Heisenbugs? How often do they happen in development? They happen very rarely, because for you to actually encounter this Heisenberg, you have to run your software in your development environment around, let's say, 1 billion times. What are the chances of you actually running it so many times? So you will never encounter this bug when you're developing software. On the other hand, when you're running software in production, in a real system, the Bohr bugs in the core of your system, they should never happen. Otherwise, you shouldn't deploy the thing in the first place, right? So the bugs that are boring never happen in the actual production system. Now, you might have some ancillary, secondary features that are breaking, like, maybe the color on your page, on your button is wrong. That's a bug, and it's reproducible, but it's not important, right? So the key here to understand is that the bugs that are boring never happen in production. What about Heisenbugs? That's a good question. How often do Heisenbugs happen in production? Is anyone who doesn't know? Can they guess?
Depends how you test it.
Happen all the time? Yeah. Oh.
Well, that's true. It could be where you're getting false positives. The code is failing, but the results are identical, especially if you have a binary output.
Well, I'm talking more like somebody calls you at night and the system is crashed, right?
In testing, that's a good thing.
Yes, but you can't reproduce these bugs in testing. You can't. In development. We'll get to testing later.
So it happens on production when you're on vacation.
Yes, but you got it. You got it. You got it. You got it right. It happens all the time, but not for the reason you might expect. It's because a bug that happens once in a billion in production, you are actually getting around, let's say, 100,000 requests every second. So the bug that happens once in a billion will happen every 3 hours. So your system is running very fast, and it's going through a lot of these cases. It's exploring this problem space much faster than you can. And so you're always hitting these bugs all the time, and you can't reproduce them. The testing of these bugs is very hard because you need to create just the right conditions and run it just enough times to increment some certain counter in a huge memory space so that you come up on the same bug. Whereas Bohr bugs testing is easy, right? If you write a unit test, that's what you're testing most of the times, right? You're testing that the core logic is correct. So the question then, the $1 million question is, the most bugs in the system are Bohr bugs or Heisenberg bugs? Who thinks it's Bohr bugs? Lift your hand.
Actually, I would go for Bohr bugs.
Excellent. Good. Good. What are you? You have no opinions? What about Heisenbergs? Who is for Heisenbergs?
In production.
In production. Yes.
Oh, so you're saying after it gets out again, depending on how well you test it.
No. I mean, let's say you have a system like a spacecraft that we built. If a bug happens during a flight, is it more likely to be a Bohr bug? If yes, lift your hand. Or is it a Heisenberg? Lift your hand. Okay. You have no opinion, my friend? Okay. Oh, so intelligent. You see? That's true. Most bugs in the systems are transient bugs. It's the bugs that just go away and you never see them again. So this is from the 1985 paper. I love the title. Why do computers stop? And what can be done about it? What can be done about it? So most bugs are Heisenbergs, which is kind of runs contrary to what people think of bugs are. Oh, I found a bug, I have to fix it. Well, you won't be able to reproduce the environment conditions for that bug to fix it in the first place. So let's get back to our space flight. All of a sudden, we get a computer error, code 500. It's the computer thinking that the error radar antenna is pointing in the wrong direction. You are in the mission control room. Do you consider this a serious problem? Is this a problem? Who thinks the spacecraft will make it to the moon still?
If it's a true problem.
This is what you get. This is on the monitor. You see it's in red. It's a problem.
Are you still getting radar results?
You're getting everything, yes.
Everything's working fine except
yes.
for the error.
Yes, you get the error.
Is this before or after the landing?
We just took off, right? We're just approaching the moon. We're still.
You could make it to the moon, but will you land correctly?
Let me put it this way: if you see an error like this on your cell phone, what do you know? Are you certain the cell phone is functioning correctly?
No.
So what about the spacecraft, which is more serious? It has 3 people on it, right?
But you can't reboot this. Actually, you can.
Yes, it's serious.
I would be concerned about it.
You'd be scared, right? You'd be concerned. I would jump out, probably.
Don't jump out.
So let's look at some of the things, some of the concepts that we used when we designed the software to make it, and try to convince ourselves that it will make it to the moon, or not. So what is restart-only software? This is a very interesting concept that talks about restarting systems. Why would you restart the system? So let's say you have an issue that you encounter in the system, right? And it's some sort of a bug. What if you restart it? How useful is restarting a system if it has a Bohr bug? Let's say the bug is 2 + 2 = 5, right? And you restart the system and it does 2 + 2 again, and it's still 5, because you. Yes, if you restart the system with a Bohr bug, it's very reliable bug, so it will always happen again. So it's completely useless for these normal bugs. Right? For these normal issues that you want to tackle, restarting is pointless because you get the same error again. And for alternative bugs, like let's say a counter is working incorrectly on your visitor side, you restart it, it works correctly for a while, you don't really care, right? It might be useful for that. But for Heisenbugs, what is the usefulness criteria for a Heisenbug? If you have a bug that came out of nowhere and you don't know why it's caused, what caused it, what's going to happen if you restart the system?
We hope that the known it's a more predictable state that you're putting your environment in because it just started, so less things go wrong when it starts. So we're expecting that this is going to go away. This is the condition to be tested usually after.
But even more to the point of, if it's very hard to create this Heisenbug, right? You have to have, let's say, 1 million different factors just be right, just the temperature be right. If you restart the system, doesn't matter if it even restarts in a bad state, right? The chances are that this bug is going to go away. It's very good chances. It's super effective at eliminating bugs that you don't know why they happen. So
it eliminates the symptom of the bug, but not the bug. Right?
yes, that's true. You don't eliminate the bug. But if you restart the system and the bug goes away, what do you care, right? If you restart your cell phone when it's slow and it starts working, you don't go to Apple and say, oh, I just restarted, it works, you're happy. So the core bugs you want to fix. Heisenbugs, if it takes you longer to fix a Heisenbug, like a year, well, maybe it's better to just restart the thing. In fact, not better, but it's required. Yes.
Sorry, I was just involved with testability and big system test and telecommunications.
Yes.
But that's not your talk. I'll let you go.
Go ahead. Yeah, testability is an interesting question, but the characteristic of a Heisenbug is it's virtually untestable, right? And we're going to show a type of a bug here that nobody in this room could have foreseen, right? Oh,
No way, we're gonna find it. Yeah.
so, as I said,
Unless you can reproduce it, in which case it stops being a Heisenbug.
well, you'll tell me if you could reproduce it or not. Well, okay. So let's finish this point first, that restarting makes Heisenbugs disappear. Everyone agrees with this? As we were flying further, this 500 error code happened. We don't know why it happened. And then we had some more alarms. Another alarm happened. And Larson is not here today, but he did raise up his thumb to give a go-ahead on the mission because he was too afraid to say go out loud. And similarly, the rest of us say go. Yes? Who would say go if you get 2 more alarms on the spacecraft? Who would say no? Turn around, go home. Right. How confident are you after 2 more alarms on the spacecraft? And you don't know what the alarms are from. You don't know what's causing the alarms. Everything is working normal.
Turning around might make it worse.
Uh-huh.
There might be nothing.
Yes.
I would try to. So this rocket is already heading towards the moon?
Yes, this is already near the moon orbit.
Okay, probably turning around would be the wrong thing to do.
Okay. Let me rephrase the question. Would you still land on the moon or just go around and come back?
I might go around a couple times.
So you wouldn't be so confident on landing on the moon, right? My point is. I mean, it's a space rocket. You got 3 errors, you don't know why, right? What are you thinking right now? You're thinking about preventing system failure, right? So the next topic we're talking about is fail fast. You see this often. And what does it mean to fail fast? And it's pretty simple. In fact, most of the things you do is counterproductive to failing fast. So you just should stop doing what you naturally are doing. You should stop trying to recover from things, and you should stop trying to fix the errors. If you encounter some error, don't try to reconnect to some system. Don't try to parse the thing you can't parse. Don't try to take a negative number and make sense of it, right? Just fail, just crush. So this principle is pretty simple. Does everyone understand it? Now you understand what failing fast is. So next question, of course, is who will handle this failure? If I don't handle this failure, someone else handles the failure. If a child walks around and cuts his toe, he doesn't go to the hospital himself, right? There is a parent who takes care of him. So each system is responsible for what it does, and it does it well. For this, we might introduce a notion of supervision. And supervision is the idea that you have certain pieces of program looking after other pieces of a system. In this case, this is an example from Erlang supervision tree, where squares are supervisors and circles are workers. You don't need to understand this. This is just an example. And one other pattern we might use for failing fast is error kernel. I don't know if anyone has ever heard of it, but the error kernel pattern says that you take this error kernel and you define it to be a part of the program that's correct, that can't fail, right? So let's say your percentage calculation logic on accrued interest for a bank account. You never want this thing to go wrong, right? So you take this error kernel and you look at how a typical software is composed of error kernels. So in a typical software, all the red stuff is error kernels and white stuff is not error kernels. So it's confusing, so let me explain. When you write a program, usually you assume that every piece of code is error-free. You don't assume it, you try to make it error-free. So you always write defensive code, you always try to protect against failures in every little piece of the system. And so what happens is your whole system is composed of error kernels, things that should not be allowed to fail. You depend on all of these things not to fail, because if any one of them fails, your whole system fails. Now here is your desired state of a system. You want to have as few error kernels as possible.
Why?
So if you have a system component that's assumed or required to be correct, you never want it to fail, right? So if that thing fails, that's it, you're gone. So you want to minimize the amount of points in your system that you want to put this assumption on, right? You don't want to worry about everything. All of these things, if they fail, that's fine. You don't care whether they're correct all the time or not. So you want to minimize these points, whereas in most software, everything is assumed to be always reliable, and that's simply not the case, right? So this is what we're striving for.
So that's the humility.
Yes.
We're not going to make the whole thing perfect. Just pick these subsets and make sure those are no ones.
Yes.
Put our eggs in those baskets.
We just recover really well.
So how do we turn this system into this one? Well, what we do is we take something that's dangerous. Let's say this piece of the system is doing some dangerous work that can fail. And we push this danger down a level. So we make somebody else do a dangerous thing, and now this thing is safe, right? So this piece now can't fail, because even if the child fails, the parent still succeeds, right? So this is a pattern called error kernel. Anyways, this is more involved for systems like Erlang, where this hierarchical supervision is given in the language. You can implement it yourself with usually some daemons or watchdogs, etc. So let's get back to our spacecraft. And as we're approaching the moon, we're executing the maneuver called throttle down, which basically turns around the aircraft and prepares it to land on the surface of the moon. And if you know this astronaut by the name of some Armstrong guy, this is a direct quote. And these are the only two places in the transcript where there are exclamation marks. So success so far. The mission is going as planned. Somehow those errors didn't cause the thing to blow up. Happy path. This is another one of those phrases that people use. And what does it mean? Well, the definition, again, is pretty simple. You assume the environment is as expected to be. You assume everything is in the best possible case scenario. So if you want your number to be positive, assume it's positive. Don't check that it's positive. Just assume it's positive. If you think of a normal case, how you want your program to work, program for that. Don't try to fix something that's not on your happy path and continue. This goes back to just failing, right? And when you fail, just record the fact that you failed and why you failed. So this is a pretty simple concept called the happy path programming, I guess, where it's very easy and it's very pleasant to program this way, I think, in my opinion. And for some reason, people don't like it. They always try to look for errors instead of the things that actually work. Now, continuing, back to our mission. As soon as we thought everything was great, at mission estimated time, 102 hours, 42 minutes, 17 seconds, 1201 alarm occurred. Does anyone know what 1201 is?
Yep.
Exactly, nobody knows. We are here in the mission control in Houston, completely baffled. 24 seconds, another alarm. It's like, oh, very stressful. 16 seconds later, another 1202. So at this point, we're almost on the moon, right? We're almost landing on the moon. We're approaching the surface. Astronauts are looking for a space to land. At this point, it's just, fuck it, let's just land. What's the worst that can happen? It's just 3 people. But I want to understand, I want you to imagine yourself in the shoes of the people in 1969, when you're the programmers, you're sitting there and you see these 3 errors on the screen, and you think, oh, maybe I did something wrong. Maybe I didn't check for some null pointer exception. Of course, there was no null pointer exceptions back then, but
This is it. Never mind. Keep going.
yes. I'll get to questions later.
No, that's okay. I was just you offered a challenge.
Okay. Error checking. So finally we get to error checking. Most of the talk has been about avoiding errors, right? So ignore them. But errors do happen, right? Sooner or later. Here's our system in the middle. And here are some other external systems we interact with. Where should we check for these errors? Because what if this guy pressed the wrong button? Or what if the database gave us some data that got jumbled and the transport layer didn't fix it? What if we needed a positive number, but we got a negative one? Shouldn't we check for those things? And if we should, where? Where should we check for those things? So I'm gonna, I don't know how to ask this. Does anyone have a suggestion of geometrically on this picture, where should we check for errors? I'm not talking about in code, but geometrically speaking on this area.
Like at the boundary.
Like
Boundary of something, which is
like this?
Yeah,
Human
so
error?
that's what the address I would
So you're
start
talking, what type of errors are you talking? Like unit, low level, specific, like a bug in A and a bug in the person and a bug in the files? Or are you talking about system or integration?
I'm talking about errors where somebody is not issuing us the expected command or not issuing us the expected input. Or we stored something and the thing we got back is not what we stored, right? Our interaction with external systems. Because this is a system we control, right? So if we control the system and we've been programming along the happy path, we've been failing and crashing and not checking for errors, where should we check for them, right?
I'd be tempted to check one layer inside the system, but not,
So like somewhere like
not at the boundary.
like somewhere here, right?
Yeah,
Like
let the boundary capture the version of truth
okay.
that came in.
Yes.
And let part of your business logic inside the system do the check.
Yes. So you let the error propagate to the business logic, and then it does the check for you, right? Any other suggestions?
Well, there's a lot of just because in telecommunications,
Yes.
I remember long ago when I was a CAD programmer and in Bell Northern Research, and I talked to one of the DMS programmers, and I said, I would love if my software only core dumped once a year. You've got millions of years between failures. And the guy said, no, we still fail, we just recover well. So,
Well,
you need to capture the stimulus. There's lots of places where you need to log things. Like you need to know what the stimulus was from the outside world that caused. I'm afraid I don't know.
Okay, let me rephrase the question.
Yeah.
Let's say the user presses the wrong button
Right.
at the wrong time.
You should definitely tell the user.
Yes, but which part of the system should reject that command? Let's say.
Or which part of the system should catch the error, or which part, of, the system
which part of the system
should tell the user that they made a mistake?
No, I don't care about that
because
part.
you got catch and throw, where you could have something fail down low, but come up with a.
But we didn't get to that part, so you're running ahead.
So
Yeah,
You could either do it in the part that cares whether that thing is bad or not, or put something around that.
Okay, I guess that's what I'm getting at. Do you catch it at the part that's immediately concerned with the input, whether that input can be wrong or not, or do you catch it in some other place, maybe dedicated
It would be
place?
better to catch it sooner.
Yes.
And
Anyways,
be able to tell so you have a better idea you may have a better idea what went wrong.
that's true. So all of those are good suggestions, and some are correct. But the first one was correct. You check for errors at the boundary. All the logging that you do is a result of the error, right? It happened. But the boundary of the system ensures that no erroneous data passes the boundary. It's like a cell in the organism, right? It doesn't let anything bad get inside of it. So we should try as much as possible to prevent everything bad from getting inside. And so if it goes inside, it's a happy path from there on. You assume it's correct, right? Which is in complete contrast with conventional exception handling, for example. So in Java, it's common to catch exceptions and try to react to them. So what is the best way to catch an exception? I don't know if people are familiar with Java or any exception handling language. How should you handle exceptions is the question.
But typically, by throwing it to the next layer up, that might.
I'm not looking for technical answer. I'm asking for conceptually. Conceptually explain to a person who doesn't know anything about programming. He says exception happened. What should I do? Should I worry about it or like?
So you typically want to handle it in the lowest level that can handle it. So you handle all of the errors that you can. I think is the appropriate response to that.
But if we're doing our happy path programming, right, and we're not checking for errors.
Doing this for sure.
Yes, that's right. If you're doing happy path programming, you don't handle exceptions. You don't care about them. So the thing you do is you're taught mostly in books is that this is how you catch it, and you should log it. That's not your concern. Your concern is to do business logic in that component. You should take that exception and ignore it, right? How you do it, that's language specific, right? So most of the time you can't do anything about them. If an exception of a transport layer happened in your business logic about accounting, what can you do? If you do catch an exception and log it, well, you will hide this error from somebody who actually cares about it. So, for example, imagine you're running your own company and your employee doesn't tell you that a pipe is leaking downstairs, and he doesn't tell you for a week, for a month, and then the next month everything is flooded. You'd rather he tell you than not. So exception handling is the same. You're swallowing up the problems. And until you start programming systems that shouldn't fail, it doesn't really matter, right? It's fine to hide these errors. And but the real way to do it is these hacks, I call them, but you would declare the method as throwing an exception, or you convert the exception to runtime in Java. This is technical. We can ignore it.
So like define to be.
Yes.
Not have to catch.
The lesson is not to catch them. And if you And if you start thinking, oh, where do I catch them, then you're the wrong person to handle that mistake. Going back to the space shuttle, during the 3 errors that we encountered last time, this is an actual measurement of an astronaut's heart rate rising from 120 to 150. And his quote after the fact was that concern was not anything of particular value, but whether we would continue the mission at all. So this speaks to the gravity of the situation, to the errors. You know, hindsight 2020, it's easy to judge. Oh, you know, this error we could have tested. You know, test this error when the person is, you know, freaking out and they still have to fly the spacecraft, right? So who still thinks this is a Bohr bug that we're facing, right? Who still thinks this is possible to test ahead of time? Well, we'll see why it is not. So next topic we talk about is external system failure. And external system failure is when something not under your control fails. So in this case,
No power.
Yes, but that.
That's pretty radical.
No,
external
that's
failure.
what you, having had experience in systems where the power went out, you put in a UPS and something and manage
But that's a good example.
a
yeah,
careful shutdown, because we'd switched the type of server, and the new server we were using self-destructed. At one time, it was a standard test on these servers to pull the plug out of the wall and make certain that it could come. And then we accidentally did that test on one of the new servers and did something like $10,000 worth of damage
Wow.
to the server. Or a component failed that cost $10,000. So I was told anyway. They could have been exaggerated.
Well, thank you for ruining one of my slides I have.
Oh.
Great. Thank you for giving away the story.
That's how you know you're getting it then.
I'll try to be quiet.
But-
I'm sorry, I did
but-
stuff like this.
Yes, so that's what I'm saying. In real systems, this is commonly done, whereas most programmers, at least the world I interact, this is not taught at all, right? So how do you handle power failure is an extreme example, but I'm thinking more along the lines you're depending on another system for some data, and the data you get is not coming. The connection is dropped, or the,
Ethernet cable got cut.
yes, and
Tripped over.
somebody comes back and restarts the system, or fixes it or mends the cable. How do you handle these types of failures? And the first step you do when this failure occurs is, we already talked about this, you crash. Because if there is an error, you don't try to handle it, you don't try to fix it, you just fail. The second step is you restart, or somebody restarts the system. And once you're booting up, you wait for the external systems to come back up. You don't do anything fancy, you just wait. Is it up? No. Is it up? No. Once it's up, you continue. That's it. That's the only 4 steps you need to recover from external systems failure. And if you take the extreme case where power goes out, this you can think of it as your own external system failure, and your crash is done for you. You just have to do the rest. So let's look at an example. Here's our system, and here's an external system we depend on, B here. Let's say B fails. The first thing we should do is try to reconnect.
Oh, yes, okay.
No, crash. We should do crash. We shouldn't try to recover. After we crash, we restart. Correct? After we restart, we wait. Excellent. After we wait, the system is up. We can continue with a normal operation. So the protocol is pretty simple, right? So now let's go back to the spacecraft error and what caused those errors. And Bob from Michigan just called us, and he came by and he said, I figured out what it is. The error was, any guesses what the error was? What caused the error?
Spiders?
It was a good guess, equivalently weird. The error was faulty documentation. So during the system designs,
That's why you should never have any documentation.
but this was
Vindicated, finally.
during the system design, somebody documented something wrong, and some part of the system got designed incorrectly. and we'll look at what this was in more detail here. This is us, NASA. All us in the room in Houston, we are NASA, right? And we contracted this other company, Grumley guys, to build us something. And when we sent them with a document, we said, "Now build us a radar system, guys. You know, we need to see where we're going in space and stuff." And we said it should be frequency locked, but we forgot to say that it should be phase synchronized. This is electronic stuff. Took me a long time to understand it, and I realized explaining this would take most of the presentation. So let's just say this was important. So here you go. This is a bug. This is what caused the bug. Write me a test for this. Somebody forgot something, right? How could you foresee this? You know, you could foresee this, but not something else.
So somebody created an error for bad documentation. You'd think instead of creating just an error that's documentation is bad, they would write a test case and prevent it from ever happening. That
Well,
seems like something
it's you know, you can only go so far before you test yourself, testing yourself.
Yes.
So there's different means of testing, and one of the early means of testing would be reviewing the document by the appropriate subject matter experts.
You know how many times this document was reviewed? You think Apollo 11 was called 11 for no reason? So my point is, we are pretty smart guys here, right? We're all smart guys, and we made this mistake. We made this mistake
Yeah.
together.
So this because I wasn't keeping track of military standards back then. I was alive though.
Yes.
Much too young to be let near a computer. I know now the military specs have also, now whether or not people follow the military specs is another question, but the military specs go through all sorts of theoretical type of coverage and things like that that only the military and the FAA bother with to make certain every little loop and corner has been tested.
I understand, but let's go back to this slide when I didn't show you the error. You know, you didn't know what the error was, right? When I showed you the error, you all of a sudden started giving me suggestions. Give me suggestions when you don't know. By the way, there's another error in this spacecraft that I'm not going to describe. I welcome suggestions on how to test that. So my point is, this is a Heisenberg. Make no mistake about it, right?
It's a requirement.
This only happens in a mission. It didn't happen in simulations, and it did. Even if it did, people disregarded it as unimportant.
Yeah, that's a different problem, though. It's not it. This type of error should have been caught during design, or when they were when it meant that they didn't do proper testing for that phase of the project.
Okay.
Anyway.
I understand your sentiment, but
No. I'm talking there's
Yes,
actually, if you're looking at rapid root cause analysis and stuff which is really ancient, that different types of bugs should be found in different places. And this is obviously the requirements weren't properly tested.
you can consider a space mission to the moon as a test, right? And the test failed. But my point is that this is a very expensive test, lives of 3 people, and we would like to avoid it. And there is never a point at which a mission stops being a test. So you can't test beyond all reasonable certainty of confusion or whatever you want to call it.
We're gonna miss something.
You're going to miss something. And my question to you is, how certain are you that you tested everything else? Are you certain that you tested everything else? I just asked you if you're confident the spacecraft is going to make it all the way there, and you wanted to turn around. So it tells me that something wasn't tested. Mm-hmm. And this is just an example, right, of what kind of error could have occurred, did occur. So let's see.
This is the same as the satellite they put up, and the whole launch failed because the Germans did their measurements in metric.
Oh,
and
no.
NASA did it in imperial.
NASA still does astronauts measured in imperial, and on ground they do everything in metric during design and
But
engineering.
But there was a satellite or something that
Yes,
failed.
this was
because
before.
of that.
Yeah.
But it would have been, well, it was a long time ago. It would have occurred after
So yes, my point is, we can't design systems that are perfect, but we must design systems that are resistant to failure. And those are two different things. You can't test in completeness, and that's a big problem, that people think they can test everything. So what we're after here is to design a system that even if it fails, because we missed something, still makes it all the way to the moon and back. And this is how we did it. We missed something, but we should still be certain that it's going to make it there. So the next subject to deal with is a long-running process. So what is a long-running process? It's precisely that. It's a process that takes a while to run. It's not done immediately. So if you're booking a trip to Cuba, let's say, you have to call ticket booth, get the ticket. You have to go online and reserve a hotel, and those things can be happening out of phase with each other, right? And this one thing comes back to you that it's done, you pick it up, you continue reserving it. Maybe the ticket wasn't available for that day, so you reserve it for another day, and then you talk to your friend to see when he is available. So you're juggling a lot of different tasks, and all of these tasks form a process, and you can go to sleep in the middle of it, and that's like, you failed for a while, and then you wake up and you continue. So the question is, how do you handle failure in these long-running processes? So let's take an example of a system at the top and the environment at the bottom. So the goal here is to track the changes in the environment with the system. So if the environment is at state A, the system should be at state A. Let's say environment changes to state B, we can follow along. Now, let's say the process crashes, the system crashes. The environment keeps going, right? It doesn't wait for us. It's not a simulation. It's real life. But we are crashed. Now we recover at state B, right? We don't know anything about state C yet. So what do? The next thing we do is we inspect the environment and change our own state to react to that environmental change. After that, we can keep along with the system, with the environment. So from a systematic point of view, not forget about programming, right? Forget about technology. If the system is unable to observe the environment for a while, it must somehow catch up to that environment, right? And this is how you would recover, for example, on a spacecraft, if all of a sudden all the computers failed. Then you start the computers, it doesn't know that it's in space, right? So this is how we're going to deal with our bug. And the bug is causing us problems. We are now getting drain on our CPU. And we do not have enough CPU to actually execute all the functions. So if we're about to land, we can crash on the moon. Here is the problem. The radar system that is working on our spaceship, if it approaches 90 degrees or about 270 degrees, it goes crazy because of the phase sync issue. It starts reporting wrong angles to our computer. And the computer is like, what is this angle? This is crazy stuff. I'm going to start incrementing a bunch of counters for this angle. I don't know what this angle is. As a result, we get load on our computer. This load on CPU time is taking away from important things like, seeing where we are and navigating the thrusters and checking the accelerometers and everything like that. And we can't devote this much time to it. So this is a real problem, right? And so the Bob person who came to explain to us the problem with documentation also explained to us that this is what's happening. At this point, how confident are you that you're going to make it back to Earth with your astronauts alive? If your computer is running out of memory, that's it. Game over. You restart it, right? So how do you restart a rocket? Excellent. So at this point, questions, and then we'll get to look at the software that we created.
So back then, couldn't they do everything by.
It's not
hand.
then, it's now. It's 1969 now. Like, you think I wore this jacket because it's 2017?
Yeah, I know I didn't have a beard. I did have a button that said "My computer understands me,"
Oh.
which my dad thought was a great joke for a little kid.
So now,
Back then, I would think that or nowadays,
Nowadays, yes.
computers are still not fancy enough that we can totally trust them with people's lives.
yeah, of
So
course.
everything would need to be, you'd need to be able to fly by wire.
Yes.
Like Space Cowboys, where I think they turned off all the stuff and just flew the shuttle with by eye.
Yes, but previous to Apollo 11, like Apollo 10, I think, could already fly on its own autonomously, and at one point they actually had to take over control, I think, because the computer failed. So you could fly by wire certain things, like maybe land at the right spot or hold altitude, but most things have to be controlled by computer because there is just for example, there's like matrix multiplications happening to correct the trajectory of the vector of descent and speed, how fast you're going horizontally before you can land. You can't go too fast, but how much should you reverse the thrusters at this point? So most things are done by computer, and certain things can be done by human, yes. But I would say you can't completely take over. So, yes. Any other questions about just the core concepts we discussed, not maybe the mission so much. No, everything is pretty clear, right?
Yeah.
Yes. Yes.
So for like actual mission critical stuff, do you really want to fail fast or anything like that?
This is how we built. This is how we built our rocket, right? I mean, you told me this is how we should build it. Are you going back on your word now?
No, I think that was something.
Okay.
Sorry, I'm having difficulties
There's always one guy that goes
Yes.
like I told you so.
That-
We should have built it another way.
We should have copied the other guys.
The reason I like this approach is because it's so counterintuitive, right? Today we always program defensively. We always try to make the thing not fail. And instead this embraces failure and says, yes, you should fail and deal with it, right? So,
No, what you're saying is still true today. It's depending on what you're doing. If you have something that just runs from back when I was in telecommunications, it's all right. If something goes wrong and you lose a phone call,
yes.
what can you do? But if the switch goes down, so when you're talking about little things, like if a phone is dropped, so they have to dial again,
Yes,
they'll
yes.
probably think it was something wrong with the set. But there's laws that says the switch can't go down.
But I would like to point out that telecommunications is not a recent system, right? It was developed pretty far back, especially if you look at most automatically routed systems, right? Before you had hand-built systems, and then in fact, telecommunications built a lot of these ideas from ground up when they were designing these systems, because they didn't want calls to be dropped, right?
So some of these, like, fail fast concept, if people feel uncomfortable with it, if you have redundancy, then it can give us some level of comfort.
Redundancy is like queues. They only delay the inevitable, right? Redundancy gives you 99.9 with 3 levels of redundancy, but there is still a chance of failure. What we're after here is no failure, right? Make no mistake. We're after that case when the redundancy fails, right? When that fails and the thing restarts, what happens next, right? So if it's a patient on the table, you see, those are different things. A redundant system doesn't mean failure-resistant system. So you can have a redundant power supply, but the code can still have a bug in it that's caused by Monday of June 24th because you are not subtracting the lunar month or something, right? Or Y2K bug, for example. How are you going to redund that away, right? So
It depends if we're talking about these Warren bugs or these Eisen bugs, right? These Eisen bugs are triggered by certain states.
these are the
And
bugs we're
then-
trying to avoid.
then if you fail fast and switch over, and that, and you preserve whatever the data was, then that allows you to keep people forward, and perhaps avoid the combination of conditions that led to the Eisen bug.
Yes, redundancy could be used as a solution to essentially recover.
It's another layer of defense.
I'm just saying that
Yeah.
with the fail fast can give some comfort to some people who don't feel comfortable with a fail fast by itself.
Yes.
So,
I think
But they're different.
if you're going to count on fail fast, which is kind of approach, I think that, which is why I think it's tricky to, and especially now that some of these ideas are coming back as our systems are being more distributed, more complex. And I think part of the difficulty is like the whole thing has to be designed this way, because for example, if you're counting on restarts or one of the other mechanisms, like you hope that's a very well exercised thing, that not some of the parts of the system have not gotten overblown to the, like their restart is like really, really slow, because that's, if restart is an important feature of resilience, then we want to make sure that it always stays fast, for example. But there's surely many other ways that the idea of fail fast can go wrong because it's badly implemented, right?
yeah.
Yes.
When you're testing, you want fail fast to make things show up so that the designer knows what went wrong. Well, fail fast in a critical system in the field, I guess you'd want to then quickly go into the recovery, which hopefully doesn't mean restarting. Like even when you've got whole redundant servers geographically distributed, if one went down, the other one, if it's in a hot standby, it might even be handling calls. So all you lose is the calls that were taking place on the switch that went down, but everything else instantly, right down to the IP address, pop back up again. Now, if that's somebody landing on the moon and losing one set, the events that happened right around it, that might not be a good recovery.
No, what I think I'm saying is that if you're going to count on the properties of this kind of resilience, where whatever it is that fell outside the box, whether we can add a layer or whatever, if we're going to count on that, it should be exercised a lot. And so I'm thinking more along the lines of, things like chaos engineering out of Netflix, where they're just like, we're going to test for failure continually, but that's also, we're going to be exercising the resiliency constantly. We're going to deliberately segment networks. We're going to shoot processes in the head. We're going to just because it's not supposed to be exceptional. Not just because we hope we found all the bugs, but it's something we actually exercise to see if, as observed, our system is resilient when we restart all the parts.
But there are ways that you can determine how well you've tested the software.
Not for these kinds of
Oh,
bugs.
you
The
can.
idea is that some of these we will miss.
If
That's
there
the
was,
whole idea.
well, there was an error, there was obviously an error message that they never tested because it popped up and everybody was surprised.
But the error
Well,
wasn't the
hold on. I'm not talking about testing here.
Yeah.
Let's talk about testing after the fact.
Okay.
My belief is that testing is a waste of time most of the time. But, because if testing was perfect, nothing would ever fail, right? So, but it does.
So if coders, I would say shouldn't have coders because if coders aren't perfect.
Yeah, they shouldn't be coders. That's my point.
No
Should be
coders,
better.
no testers,
They should be better.
those lucky users.
So, but redundancy, I wanted to point out, is conceptually a much more complex problem than simply restarting the system, right? To implement redundancy, you have to implement some mechanism of switching over the load to another system. Mm-hmm. Whereas if you fail and restart and you assume everything is good, it's very easy, right? It's very easy. You just start, you load the last state, you keep going, right? So redundancy is an additional layer, like you said perfectly, it's an additional layer of protection.
That might require consensus or...
Yes, but what if your redundancy fails, right?
Well, if you've got a hot standby redundancy, then there's a good chance that the two things are sharing the load, and when one disappears, all that's lost is the stuff that was on that one box, but everything else can reroute, can naturally, because the two of them are
Well,
resident.
That's
There are
one
different
factor.
models of redundancy, the simple ones, the complicated ones.
Yeah.
It's just an example to
Yes,
say
yes.
that, along with these concepts, you can layer other concepts along with them.
Yeah, it depends how important.
I like
Just trying to get
redundancy
rid of
it's a very nice concept. The problem we have here is that our spacecraft is limited in weight, and we can't add extra computer to it,
Well,
right?
connected to the cloud.
Yes.
1969.
Literally, you leave a wire in.
They were the first to bring it to the cloud.
So,
I
okay.
got a question. Do you want a beer?
Yes, please.
Got a repo?
So let's conclude. If there is no more questions, we'll conclude with the Apollo software itself that we wrote, basically, and the core design principles that they followed that we followed when we were building this. So how did we make use of all of these things that we talked about? So first of all, we organized our system in jobs. So we had jobs that are prioritized. We didn't allocate time slices to different pieces of software and preemptively take stuff away because it's too complicated. Programming in slices of time is complex. We're going to program in jobs. So a job is a bunch of tasks that run in sequence, right? So this, by the way, was the first implementation of such a system designed by Hal Laning, who was pretty good. Here's an example of some jobs that are running on our spacecraft, and they're prioritized from low to high. And this servicer job is run by every 2 seconds to navigate basically the spacecraft. And it's the lowest ranking job because all of these other ones take very small amounts of time, right? So all of these finish, and then this thing does its main bulk of work. So what happened in the error that we encountered? Because we kept getting wrong angles in increments and decrements, this servicer job didn't have time to finish. It didn't have time to have enough CPU time to figure out what it needed to do, and it got scheduled again. So we got a memory, almost like a memory leak, or we started running out of memory. So there's a problem. You're in a spacecraft and you're running out of memory, and the main thing that navigates your spacecraft can't navigate. So the second thing we implemented was restart protection. So here is where we're talking about what happens when we fail. The system failed. How do we recover from the system? And we write most of our system in such a way. This should be register. We write a line, we save a checkpoint, and we write a new line of code. So if the system fails here, right, we just assign new value to new x. Once we register a checkpoint, new x is saved, and then we can assign it here. So, like you were saying, the programmers actually had a button on the table that they would press sometimes during simulations, and it would restart the system. Yeah, and they were just restarting the system of the simulation of the spacecraft, and the code kept running because it kept these checkpoints. So we came from failing fast, the notion of failing fast, to a solution. And programmers are very good at coming up with these solutions. So you follow the concept of fail fast, crash. And then how you recover, that's your problem, right? Here they recovered like this. And so this gives us the ability to crash anytime we want to. And we can crash if resources are exhausted. So if we're running out of CPU or memory, don't try to fix it. Don't write a memory cleaner, just crash. And here is the procedure that was called bailout that could actually be issued by the operating code to crash the system. So it would say, oh, the CPU is, doesn't have enough resources here, or the memory is it crashed because of memory here. The memory registers are being taken over, and there is no more to issue to this new job I'm scheduling. Crash. Once you crash, we need to restart, and we will restart only the most recent copy of the job. So in this case, our servicers kept queuing and queuing and queuing. We don't need all of them because each one of them knows how to pick it up from the last one. And so in this case, if we have jobs A, B, C, D, and this one gets queued a bunch of times, well, we drop this one, and we restart that one. So all of a sudden, you see that we had a problem with memory, we restarted it, and there is no problem with memory. how did this look in reality? Here is an actual graph from the mission that we recorded. And for simplicity, we'll call this memory. And if you can see here, these spikes here are these jobs that are getting scheduled and scheduled and scheduled are not executed. At which point the system restarts us. It throws out all the extra jobs. And all of a sudden, we can fly the spacecraft again. Right? We pick up where we left off. And this parasitic incrementer keeps incrementing the counter, keeps incrementing. And we restart again, and we have enough space to do this. And after a while, when the load on the CPU decreases, when you don't need to do such massive calculations of vectors and stuff when you're landing the spacecraft, you can function pretty normally after that. So by restarting when we run out of memory, the system fixes itself. And this has nothing to do with the documentation bug, documentation problem. This fixes any Heisenberg, right? So what I was trying to, yes, but this time is sufficient to execute things. If this was not fixed, we'd crash. The spacecraft would crash. So most Heisenbergs are of this nature, that they happen rarely enough to where by restarting we can fix them. And so this was the story of our flight, drawn from these wonderful tales. Wonderful video, charming genius of Apollo guidance computer. Why do computers should start? Crash-only software, which is very interesting. This is an article I wrote about long-running processes. And then, of course, this is the report written by Don Iles in 2004 about Apollo 11 problems they encountered. And this was an actual problem that they encountered. And there was a second problem as well. So this is how they landed the spacecraft on the moon. They didn't do it through the stuff you see most today we do. They did it through clever engineering and anticipation of errors. And so at mission estimated time 102:45:50, Armstrong landed the spacecraft in the Sea of Tranquility. Excellent. Of course, there was a way back, but that's okay. This is success. The end. And for fun, this is the actual listing of the source code for the full operating system of the spacecraft.
They fit all that paper into 174 kilobytes?
Well, this is a later revision. This is for, I think, Apollo 11. The first one was much smaller.
But this machine, did they do this in assembler or?
Oh, that's a good question. There was two languages. There was Yule language, which was like an assembly language. And then there was another one called interpretive, which was interpretive language, used mostly for matrix multiplication, double precision, mathematical higher abstraction. And that thing was very slow, they say, much slower at the cost of higher abstraction. And these memories, registers were running out on registers for that language, basically. And so they had to balance the assembler language with a higher level abstraction language, and they were fighting all the time because the thing was much slower but much more expressive. And they were both created at that time, those languages. Very interesting. I don't know if I have. Yeah, one was created by Hugh Blair Smith, and the other was Charles Muntz, if anyone heard of Charles Muntz.
Not the guy who writes children's stories.
Oh, okay. Probably not. probably not the same guy. So yeah, that's the end. Let's wrap it up. Thank you.